All right, we're about to peek inside the mind of a machine. We're going to see exactly how an artificial intelligence is built to think, to strategize, and at the end of the day, to win at some of the world's most difficult games. Let's dive in. It's a question that really gets to the heart of what AI is all about. When you're playing against a person, you can practically feel the gears turning in their head. But what's going on inside the silicon? How does a machine actually reason its way through a move? And what's so fascinating is that games are the perfect laboratory for AI for the exact same reasons they challenge us humans. They are a pure test of logic. You've got clear rules, a single goal, and absolutely zero ambiguity. It's just your mind against your opponents, which makes it the perfect arena to build a truly rational, thinking machine. But here's the thing. In the world of AI research, not all games are created equal. They aren't really interested in games of pure reflex or, just blind luck. They're after something way more fundamental, a pure test of strategy. So what they do is they zero in on what are called games of perfect information. Think chess, or even simple tic-tac-toe. Everything is right there on the board for both players to see. There's no hidden information, no random roll of the dice. Success is 100% about logic. The goal isn't to create a lucky gambler. It's to build the perfect strategist. By stripping away all that randomness, what you're doing is creating a perfect, sterile environment. It's really the ultimate lab to see how a purely rational mind works when it's up against a tough strategic problem. Okay, so if the AI isn't feeling its way through the game or using intuition like we might, how does it actually visualize its path to winning? How does it even see the board? Well, it sees the game as this enormous, sprawling map. It's called a game tree. Think of it like this. From the very first move, the tree branches out to show every single thing you could possibly do. And for each of those moves, it then shows every possible reply your opponent could make, and on and on and on, charting every potential future until the game finally ends. As people, we do a tiny version of this in our heads, right? If I move here, they'll probably go there. But a machine, it can visualize this entire tree of possibilities on a scale that is it's almost impossible for us to even wrap our heads around. So how does this tree actually get built? Well, it starts pretty simply. You've got the empty board. Then, the first player's options create the first layer of branches. But then, for each one of those branches, the opponent has their own set of replies. And this is where the tree just starts to grow exponentially. With every single term, the number of possible futures, it just explodes. Now, to navigate this insane tree, the AI defines the players in really specific ways. Our AI player is called Max. Its only goal in life is to make moves that maximizes its shot at winning. The opponent, naturally, is called Min, and its goal is to do everything it can to minimize Max's chances. It is a pure head-to-head showdown. So the AI has this unbelievably huge map of every possible future. But a map is totally useless if you don't know where you're going. How does it know which one of the billions and billions of paths is the one that actually leads to a win? This is where a really cool concept called utility comes into play. Utility is basically just a score, a payoff, that the AI gives to the final outcome of any path down that tree. It's the AI's way of asking, okay, if I follow this path all the way to the end, is the result good for me or bad for me? And this whole scoring system works because these are zero-sum games. It's a simple but really powerful idea. For me to win, you have to lose. We're fighting over a fixed prize. One of us is getting a positive score and the other is getting a negative one. That's it. And this is where it all comes together so elegantly. If a path leads to a win for our AI Max, that path gets a utility score of +1. If it leads to a loss, it's a -1. And a draw, that's just a neutral 0. So this entire massively complex game gets boiled down to one simple goal. Find the path that leads to that sweet, sweet +1. It sounds almost too easy, doesn't it? Just look down every path and pick the one that ends with a +1. Well, not quite. There's a massive, almost incomprehensible problem with that plan. Let's just take a super simple game like tic-tac-toe. On your very first move, you've got 9 possible squares to choose from. That's 9 branches on our map right out of the gate. For each of those, your opponent then has 8 choices. Then you have 7, and so on. And in the world of AI game theory, there's a specific name for each level of depth in this tree, each turn taken by a player. It's called the ply. and it's a really crucial term for understanding just how big this problem gets. And here is the absolute key takeaway. As you add more turns, as you add more ply, the number of branches in this game tree doesn't just grow, it explodes. It explodes exponentially. The map of all possible futures becomes unimaginably huge, almost instantly. So if the map for Tic-Tac-Toe gets big that fast, the map for a game like chess is, well, it's astronomical. The number of possible game variations in chess is estimated to be larger than the number of atoms in the entire observable universe. Just think about that for a second. You can't just tell a computer to search that whole map. It is fundamentally computationally impossible. So, that brings us to the ultimate question, doesn't it? If the map of all possible outcomes is just too gigantic to ever explore completely, how does a machine ever win? How can an AI possibly find the winning path if it can't even see the whole map? Well, that is the secret sauce behind the algorithms that truly make these machines intelligent.